There we go. Okay, so let's do a quick recap of atomic size or atomic radius, ionization energy, the whole nuclear charge thing, and shielding effect. Okay, so you guys told me yesterday, and I think I'm going to clean this up a little bit. Let's get rid of this binding energy stuff. All right, so you guys told me yesterday that as you go across on the periodic table, the size of atoms actually gets smaller, okay? And we said that was because the number of protons is getting bigger, while, yes, the number of electrons is getting bigger, but the number of electrons in, the number of shields of electrons is the same. All of these, you have an inner core of 2 electrons, okay, every single one of them. And so what we say is the effective, or the nuclear charge is increasing, but the shielding effect stays the same. What the shielding effect refers to is any core electrons that are between the very strong positive nucleus and the outer shell, okay? All of them have the exact same amount of electrons, the exact same number of rings of electrons between the nucleus and the outer shell. Does everybody get that? Okay, so we say the nuclear charge goes up. So if it's a stronger pull, but the same shielding, then everything is going to get pulled in tighter, and therefore the atoms are going to be smaller. So now let's switch gears and think about what that means in terms of ionization energy. Ionization energy is the energy it takes to remove an electron. Does it get easier or more difficult to remove an electron from atoms that are holding them tighter and tighter and tighter? More difficult. So size goes down, but ionization energy goes up. Everybody get that? Okay. The second thing that I want to just kind of clarify is that there's nuclear charge, but there's also effective nuclear charge. And a lot of times they go hand in hand. Okay? So effective nuclear charge is simply the number of protons minus the electrons that are shielding it. So here, there's 3 protons shielded by 2 electrons, and so what's left is a +1 charge. That is the effective nuclear charge. Here, there's 4 protons shielded by 2 electrons. That is a +2 charge, and they get increasing as you go across. So not only is the nuclear charge increasing, but the effective nuclear charge is increasing. Effective nuclear charge is really useful when you're going down, okay? So let's focus on, I kind of drew in potassium, so let's get rid of that, okay? So let's focus on sodium. Here's sodium, and it has more protons. The nuclear charge increases, but the effective nuclear charge doesn't. If you look, 11 protons in sodium are shielded by the 2 electrons, so 11 protons are shielded by the 2 electrons in the first energy level and the 8 electrons in the second energy level, a total of 10 electrons. So it has an effective nuclear charge of +1. Potassium, 19 protons, shielded by 2 electrons in the first shell, 8 electrons in the next shell, 8 electrons in the next shell, +1. As you go down any group on the periodic table, the effective nuclear charge will be the same. But what's increasing? The shielding. This only had 1 shield. This has 2 shields. Okay? And all of these in that row will have 2 shields. So because the effective nuclear charge is the same, so in a sense, there's not really that much more pull because the shielding, right? Effective nuclear charge kind of takes into account the nuclear charge and the shielding. So because that stays the same, but the shielding increases, right? The shielding effect increases, the size gets bigger. So the outer electron is further away. So now let's shift to talk about ionization energy. If this electron is farther away, does it take more or less energy to remove it than, let's say, in lithium? Less energy. So ionization energy goes, so as you go down, ionization energy decreases. As you go across, ionization energy increases. And I think yesterday we even kind of related this to reactivity, didn't we? If it gets easier to remove electrons as you go down, what's happening to the reactivity of all the alkali metals? It's increasing. If it's easier and easier to remove, bing, 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 right? Okay? To where like cesium, oh my goodness, or francium maybe takes out a room. Okay? Go ahead and stop, Charles.